So today's speaker is Paolo Cascini from the Imperial College London, and he will speak about birational geometry of foliations on a complex threefold. Thank you for
thank you,
Paolo.
Thank you, Nikos, and thank you to all the organizers for this wonderful organization of seminars. I try to attend many, but I cannot do it all the time. But anyway, the initiative is really great. So thank you for giving me this opportunity. So over the last few years, I've been thinking about foliation and the birational geometry of foliation. So I would like to give some kind of survey about what has been happening in this direction, at least in the terms of minimal model program. There are many directions that are very interesting, but I will mostly focus on minimal model program, in particular, some application in birational geometry. Okay, so let me start. So what I'm going to say today, it's all based on work with Callum Spicer, and there's some works with others, but I will focus mostly with the work with Callum. Okay, so I will start very slowly, so I'm sorry for the expert that I have to deal with this. I'm going to work over the complex numbers always, and X will always denote a normal projective variety. We don't assume it to be smooth, and just in terms of notation, we take n to be the dimension of this variety. So what is a foliation? A foliation on X consists of the following data. So first of all, we need to have a covariant subsheaf of the tangent sheaf of X denoted by TF. And this sheaf will have rank R, where R is the rank of the foliation, and satisfy some properties, of course. So first of all, it's closed under the Lie bracket, and we'll see why we need this in 1 minute. And the second property, which is very basic property, is that the quotient, which we denote by NF, is the normal sheaf of the foliation, is torsion-free. Okay, why is it basic properties? Because we can always achieve this property by just taking, given any subsheaf, we can always take the saturation in such a way that this property is achieved. So this is the real ingredient in the definition of foliation, the fact that it's closed under the Lie bracket. Okay, so in terms of notation, before I talk about some basic properties, we have a sequence given by the normal sheaf, and we denote by omega-1f the dual of the tangent sheaf of the foliation, so in other words, the sheaf defining the foliation. And more importantly, this will be the guy that will play a role in what we're going to do. We denote by kf one of the A divisor for which the associated sheaf coincides with the determinant of the dual of the tangent sheaf, sorry. So in the same way that the canonical divisor of a variety, it's useful to understand the birational geometry of the variety, this divisor here, the canonical divisor of the foliation, will be useful somehow to understand how to, well, maybe classify, it's a big word, but how to understand some kind of rough classification of foliations. Okay, so first of all, this is a little bit technical, so bear with me for one moment. I want to define the singular locus of a foliation. And since I know that, I mean, X is not necessarily smooth, when I take the rth wedge power of omega-1 of X, where R is the rank of the sheaf, it might not be reflexive. So we take the double dual of this sheaf, and we tensor by the dual of the canonical sheaf of the foliation. So it's easy to check that there is induced linear map, natural induced map into OX. So why do I need this? It's because the singular locus of F is by definition the co-support of this map. So if this is not clear, it doesn't really matter because, for instance, if X is smooth, this coincides with the locus, and this is the classic way to look at the singular locus of a foliation. This coincides on the locus where the normal sheaf of F is not locally free. So when X is singular, these two objects do not really coincide, but it's not going to play any role in what we're going to talk about today. So very easy remark, this object, since we're taking the saturation of, we're assuming that this sheaf is torsion-free, this object always has singularities, which I've got to mention at least two. It's a little bit like when we take varieties, we always take, usually we always take a normalization, and the normalization will have a singular locus which has codimension always at least 2. So taking saturation is somehow equivalent to take the normalization of a variety. But more important, why do we need a closure with respect of Lie brackets in the definition of foliation? Well, this is a standard theorem. It's a very classic theorem in differential geometry. It's due to Frobenius, saying, suppose that we are away from the bad locus. So let's take a point which is not contained in the singular locus of the foliation, nor contained in the singular locus of the variety. Then we know by Frobenius theorem that there exists always an analytic open neighborhood U of X, and an homomorphic map phi into Cn minus R, where n is the dimension of X and R is the rank of the foliation. So this is the co-rank of the foliation, such that the foliation in this neighborhood is induced by this function, this holomorphic function. So in other words, the foliation is just the relative tangent bundle of this fibration. So the reason why this is important is because locally, analytically, everything looks like a morphism. And what is a leaf? A leaf is just something that locally, analytically looks like a leaf. Sorry, it looks like a fiber of phi. Now it looks like this is not well defined because it depends on the point, it depends on the choice that we make, but actually it turns out that it is well defined. It does not depend on any choice, local choice that we make. And all this is very, very standard. So please interrupt me if you have any question. I will give an example of a foliation. Here is a typo, so integrable. The sample of algebraic integrable foliations. So what is this? Well, this is an easy example in some sense, but this is itself already very interesting. Any fibration in algebraic geometry, so by fibration I mean something surjective between normal variety with connected fibers, induce a foliation. So how do we do this? Well, we just take the kernel of the differential. Now this subshift here might be not saturated because it's possible that the fibration might have non-reduced fibers. So for this reason, we take the saturation to avoid the fact that the quotient might not be, the normal shift might not be torsion free. So this guarantees that the first property is satisfied. I mean, the second property is satisfied. Then being closed by Lie bracket follows as an easy calculation. So let me give a little calculation. Okay, so in case we can do this in general, but let's focus in the case where either Y is a curve or F is equidimensional. All the fibers have the same dimension. Then in this particular case, it turns out that the canonical divisor of F coincide with the relative canonical divisor of the fibration. So in other words, Kx minus the pullback of Ky, plus an error. And the error is supporting the multiple fiber. So more precisely, if P is a prime divisor, then we denote by LD the multiplicity along D of the pullback of P. And the error terms is given by this factor here. So of course, this will be for almost all divisors, it will be 0 because LD will be equal to 1 for almost all vertical divisors. So there will be only finitely many on which this is supported. So studying the Barasian geometry of this shift here, of this divisor here, or studying the minimum model program for this divisor here, in particular implies to study the minimum model program for this divisor here. So even if we consider a morphism for which the fibers are all reduced, this is already something quite new. There are many papers, many works that work about relative minimum model program, but rarely one can see the minimum model program for this divisor here, as far as I know. We usually just take a relative minimum model program, we don't really make this one F, we just make it relatively in F. So from this point of view, this is quite new, and we will see later some application of this, which leads something new even in Barasian geometry. So as mentioned, these are called algebraic integrable foliation. They are very, very particular example, but still of foliations, but still very useful. And now the question is, so in general, can we try to classify foliations? What does it even mean to classify foliations? So this is a very vague question, but like in algebraic geometry, we usually answer this question by saying, but at least can we build a moduli space of foliations? And this looks like a natural question, but somehow it hides lots and lots of details, lots and lots of problems. So the main problem, as far as I know, is boundedness. So we expect, or at least we hope, that many of the boundedness property for varieties apply here. So for instance, varieties general type have bounded volume, but we don't know if... Sure.
Could I ask, what do you mean by moduli space? Is that moduli of foliations on X fixed, or what are the points of this moduli space?
Even that, it's not clear. Yeah, you can fix X and you can vary the foliation, or you can take both the deformation of X and the foliation. But keep in mind that all this, as far as I know, they're very, very open. Even considering only algebraic interval foliation, as far as I know, they are very, very hard problems. So we really know anything. So whichever particular case, it's already interesting. So for instance, even assuming X is fixed, because you don't know how many variations they might have and so on. So even for surfaces,
but so there's no like most, but like from the point of view of birational geometry, there's no most natural moduli problem, or?
I mean, we would like, since it's a very open question, we would like to make it as easy as possible. So the question is, assume that X is fixed. This is already interesting enough. I suppose that the variety is fixed. But the problem is that when we start considering this problem, we start looking at the moduli functor associated to whatever numbers we are fixing, whatever invariants we're looking at. And the first question that comes to mind is this functor bounded? And even this, it's very, very open. There are many interesting results. So I just mentioned some. I don't have time to go into details. So Perez-Valdi, as far as I know, it's the first one where there is some results in this direction. Then more recently, Hakon and Langer considered this problem. And then Yan and Chen has also interesting results. And much more recently, Spice and Svaldi have some results. But all these results still do not answer the question of boundedness, even in the case of surfaces, even for algebraic integral foliation, as far as I know. So it's so this is more like a dream rather than, at least at the moment, it's more like a dream rather than a real question. We don't really have a conjecture as far as I know. Okay, so this is the motivation in some sense. And I would like to talk about the birational geometry. So as usual in birational geometry, we need to work with singularities. Why? Because, well, singularities are very natural, even more for foliation. I'll explain one of the reasons in 1 minute. So, but before doing that, let me just give a remark. Let's suppose that we have a birational map between normal varieties, or even dominant map, but we're not assuming that this is a morphism. So it could be that it's a blow up, but it can be even a contraction of something. So it really can be anything. And let's suppose that F is a foliation on X. Then there exists a unique foliation, which is naturally defined on Y, just by taking, so for instance, let's suppose they're birational. So there is an open Zariski subset, which is isomorphic for both of them. So in particular, we have a foliation on an open subset of Y. And then there is a unique way to extend it to Y, I mean, the foliation, in such a way that the properties are satisfied. So all this is fairly straightforward. So this means that we can jump from one variety to another in birational geometry. And yeah, maybe I should have said, at the very least, in terms of answering your question, you need to assume that, for instance, the canonical sheaf is ample or something like that. Otherwise, it really makes it too hard. So the question is, can we make it ample or something like that? But before doing that, can we make the foliation smooth? And of course, there is no way we can do that. I mean, even consider this very, very simple example. Suppose that we have a surface or even a pencil on a surface, which defines a foliation. Then singular points of the foliation coincide with the singular points of the fibers. So if we blow up the fibers, it surely doesn't help. I mean, we create even more singularities if we blow up fibers. We don't want to take, I mean, blowdowns, because those are not easy to control. So it's really hard, I mean, it's really impossible, sorry, to resolve singularity for foliations. But this is not a problem. I mean, we need to live with singularities, but that's something that we know for a long time, even for varieties. So thanks to the work of McQuillan and many others, we have an idea what singularities might appear in the world of foliation, at least in bidirectional geometry. So if we know the definition of canonical variety, then this might look very, very familiar. We say that a foliation F is canonical if, first of all, as usual, we assume KF is Coulter, so we can allow pullbacks. And for any bidirectional morphism, I'm not assuming Y it's a log resolution because we don't know the existence of a resolution. But let's just take any bidirectional morphism. Then the difference between the canonical sheaf or the canonical divisor of the foliation induced of Y and the pullback of the canonical divisor of F, of course, it's support an exception divisor because elsewhere there is a morphic. But what we ask, exactly like for varieties, is that the exception divisor is effective. We're going to see a more general context of singularities. But for a moment, let me comment on this. So let's consider the previous example. So a very, very simple example where X, a surface mapped to a curve. Then to say that the foliation is canonical is exactly the same as saying that the reduced the reduction of any fiber has simple number crossing support. So this can be achieved. If we take any smooth surface which admits a curve, emits a morphism to a curve, we can surely blow up in such a way that we can obtain a family which satisfies this property, which is has fibers with simple number crossing support. We are not assuming that the fibers are reduced. We are not taking semi-stable reduction because we want to have only bidirectional maps. And so surely semi-stable reduction will not be in our context. But surely we can make it canonical. Okay, so now the question is, given a foliation F on X, sorry, I should say on X, can we find a bidirectional morphism from Y to X such that induced foliation is canonical? This is a natural question, a very natural question, but it's very much open as far as I know, in general. So there is an old theorem by Sardenberg, we can be translated in such a way that it gives a positive answer. Of course, at the time, he was not talking about canonical singularity, he was talking about reduced singularities, but the idea is very almost the same. So, and the answer is yes for surfaces. And for threefolds, the answer is also yes. But let me just say that for rank equal to 1, this is the result of McQuillan and Palazzolo. I would just say that in order to achieve such a resolution, we need to apply weighted blowups. And so what is the problem about applying weighted blowups? The problem is that even though we might resolve singularities of the foliation, we might, even if we start with something smooth, we might induce some singularities on the variety Y. But this is not a problem because the singularities are very well understood. So this is optimal result, but it's really useful result. I mean, we really can understand how threefolds can be somehow desingularized, I mean, resolved in terms of foliation singularities. For rank 2, the situation is even better. There is a result by Kano which tells us that we can even make Y smooth. So either in any case, we can make Y with quotient singularity, very easy quotient singularities. So the situation is good enough for us in terms of bidirectional geometry. Okay, so now that we have some form of resolution, what can we do with that? So the problem is that, as usual, we want to apply induction. So this is a usual problem in bidirectional geometry. When we talk about induction, we need to use adjunction. And when we use adjunction, we need to introduce pairs. That's the price to pay. So as usual, it becomes technical, a little bit technical, because we need to work with a larger category. But bear with me only for a few minutes, because hopefully we will get through this and we can even forget about this. So I need to talk about what is the category of foliation that we want to talk about. So we say that a foliated pair a foliated pair consists of the data of a foliation F on a variety X, which is normal, and a Q divisor delta, which is effective on X, such that, exactly like before, we ask something to be Coulter so that we allow pullbacks. So in this case, KF plus delta is Coulter. So like in bidirectional geometry, classic bidirectional geometry, if you don't like pairs, we can take delta equal to 0. But some of the results I will mention later will make not much sense in this generality. Okay, so this is very vague, so I'm sorry with the expert about this definition, which is not quite correct, but nevertheless, we say that the divisor E on X, it's invariant if it's a union of leaves. This is not the classic definition, I just wanted to make it easy. So in the case of f being algebraically integrable, so in other words, induced by f aberration, then B invariance is pretty much the same as saying that it's vertical. So in other words, the image of the divisor is not the whole codomain Y. So these are easy objects to study. But why do I do this? Well, the reason why we do that is because we'll see in a moment that a junction behaves differently, whether E itself invariant or not. So before I talk about junction, let me talk about log canonicity. So I would say that I would just denote by epsilon E equal to 0 if E is F-invariant. Otherwise, epsilon E is equal to 1. So we will not need this number for very long, but just to make the definition of log canonical. And then I will try to justify why this definition behaves like this compared to the usual definition of log canonical. So what is a log canonical pair? Log canonical pair, it's a Fourier pair such that for any bilateral morphism like before, we can write the canonical device of Fy, which is the strict transform of F, plus the strict transform of delta, minus the pullback of Kf plus delta. As usual, the difference is a device which is supported on the exception locus. So this formula, it's always true. What we need to do is to add some condition on the coefficients. And the coefficient is that AI is always greater or equal than minus epsilon I. So in other words, it's greater or equal to -1 if EI is invariant, is not invariant, sorry. And it's greater or equal than 0 if it's invariant. So if we take F to be the trivial foliation, so in other words, the foliation for which Kf is equal to Kx, then this is the standard definition. Why? Because no device is invariant, so whatever we always did, it still works. So this is some kind of generalization. And now you're free to ask, why did I use -1 instead of minus epsilon I? So I don't know exactly what was the motivation, the original motivation, but the way I like to say it is that this is very vague. And this is not even a theorem. It's true in many cases, but it's, as far as I know, it's not been proven for generality. We hope, and it's true for many cases, that there exists some kind of adjunction for foliation. So suppose that, like usual, let's suppose that S is an upper surface. Let's suppose it's normal. Let's make it easy, sorry. Then we can always restrict the foliation to S. There exists an induced foliation on S in such a way that if we restrict Kf plus, so we distinguish two cases. If we take S to be F invariant, then we just restrict Kf. Otherwise, we restrict Kf plus S. And what we're going to get is this formula here, where delta S somehow coincide, or not coincide, but is similar to the different of Sokurov. So I measure how singular the objects are. Now, of course, for Sokurov, he only cares about the singularities of the varieties. Here we need to look at the singular locus, also the foliation. But modulo this technicality, all we care about is that delta S is effective. So in other words, we can apply inductions. In our theorems, whichever theorems we want to prove, and we'll see some later on, we can apply induction. And so we can use this formula to compare X to S, where S is an upper surface, and somehow live from there. So as I say, the reason why we distinguish two cases is because the junction for sure does not work exactly the same in these two cases. So we really need to have different formulas for different cases. Any questions so far? As I say, please interrupt me if there are any questions. Okay, so let's start to talk about results. Let's start to talk about what do we know about this foliation. So let's start to go through the steps of the Minier model program as usual in Brashian geometry. So the first step after Ronaka's theorem, the first step is the bend and break, Morris bend and break. Morris bend and break tell us that if we have a curve which is negative with respect to the canonical divisor, then we expect to find rational curves, at least in the singular locus, in the smooth locus, at least if we assume that the variety is not too singular. So here the situation is very similar. So let's suppose that we have a foliation with canonical singularity. There are many, many generalizations to the log canonical world, but as long as the theorem is interesting enough, I will consider only foliation without delta. Let's suppose that the X is a point of a curve, C, such that the most important thing here is that it has negative canonical degree with respect of f, the foliation. Then we also assume for simplicity that x is not contained in the single locus of f. And also let's fix a divisor h for what I'm going to say next, but this is not very important at the moment. What is important is that, at least conjecturally, we expect the existence of a rational curve xi, passing to x, and which is moreover tangent to f. So you can imagine what tangent means, but technically almost saying, suppose that everything is smooth, which is not true. It means more or less that it's continually for f. So this is not going to be exactly precise, but it gives an idea of what it means. And then in order to understand the cone theorem, we have a bound on the degree of the curve with respect to the ample device we fixed. But this formula is not going to play any role for us, so I'm going to leave it there without commenting on it. What is really important here are two words. The first is rational curve, and the second one is tangent. We want to find a curve which satisfies these two properties. Okay, and the reason why this bound is useful, or this fact here is important, is because exactly like in the Morris cone theorem or all its generalizations, also here the generalization in the low-canonical world, we expect that there exist countably many rational curves, such that the cone of curves can be decomposed into a part for which we don't know anything, the part which have no negative degree with respect of the canonical divisor, plus a part which is closed. It's closed because, I mean, where the cone of curves is really closed because it's spanned by these curves Ci, which are rational and they're tangent to the foliation. So this, again, these two words are important here, and we will see why in a few minutes. I don't want to say too much about this because, first of all, it's not very different from the usual cone theorem, and second, because I'm not going to be too technical for what I'm going to say next. So what really matters is what I mentioned before. If you have a negative curve, then we can make it rational and tangent. Okay, so what do we know so far about this theorem? This conjecture, sorry. First of all, both these conjectures are true for foliation of rank 1. This is a very nice theorem by McQuillan, which is actually much more general than what I stated, but this is already very useful in terms of Miyamoto program. Then in his thesis, Spicer proved the case of rank 2 on a threefold. We generalize it to log canonical pair, or at least pairs which have 9 singularities, but I mean, I don't think it's just a technical result, so I'll leave it there. And much more recently, actually, this is still a work in progress. With Ambro, Shokurov, and Spicer, we prove these theorems for algebraically interable foliation. Now, you might wonder why these people joined together to get this result. So the goal of this was really to prove, I don't have time to talk about this. I'm happy to talk about this in other occasions, but I'll just say very vaguely, there is a very nice formula which is due to many people, and generalized Kodaira formula for elliptic fibrations, which is the canonical bundle formula, which compares, which gives you an understanding of the singularities and the moduli part of a fibration. So usually this canonical bundle formula works for fibration which have relatively trivial canonical divisor. So this is not about foliations. This is really about, varieties in general. So, and this is a program that was started by Shokurov quite a long time ago, actually. So can we extend this formula in the world of any fibration, without any assumption on the fibration, without assuming that it's relatively Calabi-Yau or anything like that? So the answer is yes. It turns out to be very useful to prove many results, or at least to make it a very nice generalization of the world before. So for instance, one of the results was due to Ambro, which was about nefness of the moduli part. So this is can be generalized to any of these fibrations, and somehow the proof it's a different proof. It works even in the F-trivial case. So it does not use variation of Hodge structure. It does not use anything technical. It only uses the bend and, well, maybe the bend and break, it's also technical, but only use birational geometry methods. So somehow we are very happy about this. But let me continue to talk about minimum model program. I will say a few words about how to prove this kind of results. But before doing that, let me remind you what is a uniruled foliation. So it just means, well, you can imagine, uniruled variety is a variety which is covered by rational curve. Uniruled foliation means that the variety not only can be covered by rational curves, but these curves are tangent to the foliation. So exactly like in the case of varieties, we can characterize foliation which are uniruled. So by combining together results by Miyooka and then much later by Campana and Pound, we know that the foliation is uniruled, if and only if, at least assuming that F is canonical singularities. If and only if Kf is not Z-effective, the canonical sheaf of F is not Z-effective. So it's not the limit of big divisor. Okay, I hope I mentioned the names correctly. So let me give an idea of how this proof works, of the Kohn theorem in general, and how I expect it will be proven even in general. So the idea underlying these theorems is this, more or less, at least these theorems here. The idea is this: if it's not Z-effective, then we have plenty of rational curves, and we can just use these results. Of course, there's more that needs to be done, but this is already enough to start. When Kf is Z-effective, since it's negative on some curves, then there must be an upper surface on which this curve is negative. And this upper surface will contain the curve, of course. So what we do is to apply induction on the dimension and adjunction. What is the problem? The problem is that we have no control on the singularity of this upper surface. So this is where the technical point of view works. And this is why this is a conjecture in general, but not a theorem. But what we do here, it's really to try to fix the singularities. Of course, when we try to fix the singularity, we need to be careful because we might lose, I mean, there might be some extra factor that comes to play in the canonical divisor. But all the ideas relies on this simple step. We rely on some hypersurface on which things behave well. Okay, so let me say a few words about this. So the way that we prove our results is just by running a relative minimum model program, the standard minimum model program. And then once we make things relative in F, we note by the Kohn theorem that the curves on which is negative must be vertical. And so the divisor, which the moduli part becomes an F everywhere. So it's very, very vague, but this is why the Kohn theorem can be used for, the Kohn theorem for foliation can be used for, to study varieties. Any questions so far? Okay, great. So let me continue. I would like to continue talking about birational geometry of foliation, at least in terms of the program. So let me assume from now on that Kf is Z-effective because, well, because for Kf not Z-effective, we already have a good understanding of the birational geometry thanks to the result of Miyooka and others. So what can we do in this case? So let's do it a little bit more general, just because some of the theorems later on will be stating the generality. Let's suppose that F delta is a log canonical foliated pair. As usual, if we take delta equal to 0, this is already plenty of examples to study. Let's suppose that Kf plus delta is Z-effective. Then what we expect to be true is that there exists a map, birational map, from X to Y, in such a way that the induced divisor, free divisor, is an F, as usual, exactly like in the minimum model program. And of course, this is a typo. Fy, sorry, this is, I don't know why it came out like this. The corresponding pair, it's called the minimum model. So we are looking for minimum models of foliations. And this is, if we really hope to find a moduli functor for foliation, this is something we need to go through. At least if we want to imitate the construction of the minimum of the moduli space for varieties after Kohler and Schäfer-Baron, this is something we need to go through. Okay, so for dimension 2, this is, I mean, we know quite a lot. The minimum model program works. It's the main results are due to McQuillan and Brunel and Mendes. I'm sure you forget many people, but pretty much everything we expect to be true is true. In other words, we can contract rational curves in such a way that the canonical shift becomes an F. The price to pay is that X prime is not smooth, but has chaotic singularities, so it's still under control. On the other hand, the bad news is that abundance is false. And this will create for us quite a few problems, which we're going to investigate later on. So what does it mean? It means that there exists a foliation F. There are many examples, but this is one particular example for which Kf is an F. Actually, it's positive on every curve, but it has no section whatsoever. I mean, no multiple of Kf has sections. So this is by looking at the Hilbert modular surface and by looking at the foliation induced naturally by these surfaces. There are also cases where Kf is bigger than F and is not semi-ample. So abundance really fails from every point of view. There is a work by McQuillan which generalizes, so I should have said, of course, in dimension 2, the only interesting case is rank equal to 1. And if we are happy to work with Cauchy singularities, then McQuillan proves the existence of Miller models in any dimension. So at least in this case, we do have a Miller model. So the question is, how do we generalize these results? Okay, so for now, for at least for the time being, we work, actually, yeah, I think for the end of this lecture, we're going to work in dimension 3. We consider 3 folds. So what is the Miller model program? So we take an array of the cone, which is Kf negative. So in other words, spanned by the classes which are negative with respect to Kf. And we define the locus of R as the union of all the curves inside R, or some, I mean, yeah, some curves which are numerically equivalent to a given one, to a given cycle. So one thing that we already know is that this is a proper closed subset. Why? Why is it proper? So it's not trivial. I mean, modulo what we already know is trivial, but it does not follow just by definition. Why? Because it's not empty, and this follows from bend and break. The fact that Kf is negative on R implies that there exists a curve on which is negative. And so it's not empty. And also it's not equal to X because we're assuming that Kf is not ipse effective. So this is easy to show. Also, it's not hard to show that it's a Zariski closed subset of X. So we can really distinguish 2 cases. Since we're in dimension 3, it's either a curve or a surface. So again, this result works in a more general setup of log canonical singularities. But in the case of foliation of rank 1 or rank 2 in variety of dimension 3 without any assumption of the singularities, we know that besides log canonicity, we know that we can contract this locus of R, this locus where Kf is negative. So what does it mean? It means that there exists a branch morphism from X to Y between varieties. Y is really a genuine variety, it's not an algebraic space, such that the exception locus coincides with the locus of R. So this is a particular case of the base point free theorem. Usually in variation geometry, we first start by the base point free theorem, but we know that base point free theorem in full generality is false, and then we have this theorem. So here we prove directly that we can contract the locus of R. And if the locus of R, the locus of R, it's a curve, so it's dimension 1, then we can flip it. So in other words, we can find another variety, another threefold X plus, which also emits a morphism to Y, where Y is the target of the contraction, in such a way that now the curve becomes positive on this. So this is, I'm not going to say too much, it's the usual flip, but this is it's a surgery, which is if the locus of R is a curve, this is an isomorphic on dimension 1. Everything is an isomorphic on dimension 1. So we really remove a curve and add it again in such a way that Kf has positive degree on this curve. Okay, so this is a good start. So if the locus of R it's a divisor, it's a surface, then we contract it, and the idea is that we just replace X with Y. Instead, if it's a curve, then we replace X by X plus because Y is too singular to continue to work with. So this is the standard algorithm in Morris program. Okay, so now the question is, how do we conclude? How do we get a Miller models from these steps? So we need termination. So with Spicer, we proved that special termination holds. So in particular, if f is general type, if kf is big, then the program scaling terminates. So this means that there exists a Mia model under this condition. Then Spicer's Valdi proved that termination holds for rank equal to 2 foliations. And we prove, but this is also somehow in the work of Michael, the termination holds for rank equal to 1 foliation. So in full generality, we have a Mia model for foliation in dimension 3. There exists a Mia model in all these cases. So in any case, whatever foliation we start with, we can always find a Mia model in dimension 3. Okay, so this is what has been happening over the last few years. Much more recently, this is not hard, but we prove it also for algebraic integral foliation. So foliation in any dimensions defined by morphism. So why is not hard? Well, because we used existence of flips after BCHM. And the only hard thing about this program is to understand singularities. So log canonical foliation defined by algebraic integral morphism, defined by morphism, by foliations, do not correspond to the fact that the variety is log canonical or the pair is log canonical. So we need to understand singularities. That's the only work that was involved in this program. It's just somehow check that everything behaves the way it should behave. Okay, so a few other results in this direction. So with Spicer, both in rank 1 and rank 2, we proved some version of the base point free theorem. So what does it mean? And so here I really need to work with pairs. I cannot take delta equal to 0. Why? Because I'm assuming it's log canonical, but like in Kawamata's base point free theorem, we assume that delta is equal to A plus B, where A is sample and B is effective. And of course, we need to assume that KF plus delta is an F. And here, of course, I'm writing something which makes no sense. Then the theorem says that KF plus delta is semi-ample. I guess everyone knows that it's an F, if you assume it's an F. So what we prove is that the base point free theorem holds. Some multiple KF plus delta is semi-ample. So this is a little bit strange. Why? Because I mentioned before that abundance is false even for surfaces, even if you assume that KF is big enough. So why is it true here? Well, the reason is because if we try to write, okay, this is a little bit technical, so I will not spend too much time on it. But if we write delta as A plus B equivalent to epsilon KF, what is going to follow is that even if epsilon is small, F delta is not going to be log canonical, which is very different from what happens for varieties. If you choose epsilon small enough, if you start with the variety which is log canonical, the perturbation is still going to be log canonical. This is not true for foliation. And the reason is because it's very possible that B contains invariant divisors, and this makes a huge difference. So I'm not contradicting myself. I really, I still think that the abundance fails for KF, big and F, but nevertheless it's true if you add something which is satisfy this property. Any questions so far? Okay, great. So this is a very old theorem, a very old result by Kiel. Well, of course, he didn't care about foliation, he cared about something completely different. But we realized that if we take his example in the 99, it's a very simple example. Well, actually, to prove all the details, it's not so simple, but the example itself is quite simple. And it turns out that abundance is false even if the foliation is algebraic interable. So this plays a role in what I was saying before. We can make, with the cone theorem, it's true. Bend and break is true for algebraic integral foliation, but abundance turns out to be false. And somehow I find this very interesting because, well, there are many things that are hidden, and we need to find a replacement. We do need, I don't know if I will have time to talk about canonical model. I hope so, but we need to find a compromise. And it's not going to be just trying to hope that things work well, because even for algebraic interval foliation, things can go quite wrong. Okay, so on the other hand, and this is what I was hiding before, in some cases, abundance is true. So in the numerical trivia case, At least in dimension 3, I will mention more results later on, but at least in dimension 3, abundance is true. So if we know that we have a log canonical foliated pair on a threefold, such that kf plus delta is numerically equivalent to 0, then kf plus delta is semi-ample. So in other words, it's torsion. This is the equivalent of a theorem by Kawamata for varieties. Actually, our proof is not a simple consequence of what we were saying before. We really do study case by case by looking at the classification. So our proof is quite tedious. But why I find it interesting? The reason why I find it interesting, because in the canonical bundle formula, this is a little bit of a technical comment. In the canonical bundle formula, we know by Ambrose theorem that we can expect the moduli part to be not only in F, but good. So we should expect it to be semi-ample. And this should coincide with the numerical trivial case. On the other hand, abundance in Singularieties is false, even for algebraic interable foliation. So in the Sokurov picture, where we take any fibration, not only relatively trivial fibrations, abundance seems to be false. And so this contradicts a conjecture due to Sokurov. So somehow there's something here where numerical trivial it's okay, but if we go in any other nth dimension, things can get quite bad. So somehow I think that this should be explored more. So I'm just going to say there are many versions of this result, some of which came before, like the result by Loré, Pereira, and Touzé for co-rank 1 foliation. Some results came later for co-rank 1 foliations, and which is due to Duell and then Duell and O. There are many, many interesting results which work in any dimension, which are much more powerful than ours. The advantage for ours is that it works in dimension 3 for rank equal to 1 and 2. Okay, so unless there are any questions, I will start talking about how two minimum models are related. And why do I care? Well, first of all, I think it's quite an interesting question by itself. Why minimum models are related to each other? How minimum models are related to each other. But also, more importantly, if we want to construct a moduli factor, we need to somehow understand canonical models. And if, as I said, canonical models might not exist, so at least we can ask ourselves how two minimum models are related. So, and for varieties, we know the answer thanks to Kawamata. So this is a result, now it's quite a classic result by now, which says that if you have two minimum models, so in particular, I'm assuming that the singularities are terminal, then if they're birational, sorry, I should have said that if they're two birational minimum models, of course, otherwise it makes no sense, then we know that there exists a sequence of flops which connects one to the other. And this is very interesting because it's very possible, we don't know if there are varieties which are made infinitely many minimum models, at least if they're not of general type. And we can ask ourselves, okay, but if we have lots of them, how are they connected within each other? And we know that the answer is given by flops. So can we ask a similar question for foliations? Well, yes, we can. Now the answer is, what is the answer? So the first results, this is due to myself and Spicer, but it's just, it's more like a remark more than a theorem. So let me consider a case of rank 1 foliation. So let's suppose that the X is a Kilty threefold. This is not very important, but what is really important is that the foliation has canonical singularity. Like in Kawamata's theorem, we need to assume that the minimum models are terminal. KF is third effective, otherwise we cannot talk about minimum models. So let's suppose that we have two minimum models. So is it true that they're connected by flops? Well, actually, it's even easier than that. It's not only they're connected by flops, but actually they're connected by isomorphism. There's only one minimum model. So there exists an isomorphism, which makes the natural diagram commutative. So the diagram is commutative. Okay, so in other words, we cannot find more than one minimum model for foliation of rank 1 on a threefold. Let me give a very brief proof. Sorry, maybe this is going to be a little bit technical, but just because maybe I should say one, I should talk about one proof, and this could be the only one if I don't have time. So very briefly, let's suppose that A1 is an ample divisor on X1. Let's take the strict transform of A1 on A2. So what does it mean that they're isomorphic? It's exactly the same as saying that A2 is ample. Why? Because if we take the proj of A2, you coincide with the proj of A1, and so it turns out to be isomorphic. So actually, it's enough to show that there is no curve C on X2 which satisfy these two properties, that F2 is the canonical divisor of F2, where F2 is the foliation induced on X2, it's equal to 0 on this curve, and A2 times C is less than 0. Okay, what is possible to show, and this is using a theorem by Bogomolov and McQuillan, is that C is F2 invariant. It's invariant with respect of the foliation on X2. And it's also canonical center. So what does it mean it's a canonical center? It means that there is a valuation which has discrepancy equal to 0. So in other words, the coefficient we were seeing before is equal to 0, and the center is equal to C. Now, by the negativity lemma, this implies the discrepancy, if it's not an isomorphism, if X1 and X2 is not an isomorphic, and since we're assuming this, it cannot be an isomorphism, the discrepancy of F1 with respect to E is less than 0. But the canonical foliation means that all the discrepancy must be greater or equal to 0. And so this is the end of the proof. So as I say, this is really more like a remark rather than a proof. But I was quite surprised when we thought about this, because somehow it says that there are no flops coming from joining two mirror models. And actually, things turns out to be okay. Sorry, let me just say a few more remarks. There is some work in progress about rank 2 foliation. So we haven't written down all the details, but collaboration with a student of mine, Rotnes and Callum, we proved that for rank 2 things are very much like varieties. Mirror models are connected by flops. But let's go back to the rank 1 case. So thinking about that, we could have a foliation which has an F canonical divisor and which has only one curve on which it's 0. So this would be a mirror model, but why can we find another mirror model by flopping the curve? So the reason is because flops do not always exist. So we found an example of a foliation which do not admit any flop, even though there should be a flop because there is a curve on which it should be equal to 0. It's an extreme array on which the foliation is equal to 0, but there is no flops. And the situation is even worse, unfortunately. There is no canonical model. So maybe you can ask me why, I mean, we already knew that there were no canonical models for surfaces because of the case of big and F. Well, at least in the case, even though KF is not semi-ample, but at least we can contract the curve. It's possible that we contract the curve and we get something which is as good as a canonical model. It's not, the canonical divisor of the foliation is not a pullback of something coming from the canonical model, but it's very much like a canonical model. Here, the situation is very much worse. Not only we don't have a canonical model, which is it's a variety, which is algebraic. We cannot even find an algebraic space which contracts curves on which the canonical shift is equal to 0. And this is surely going to be a problem when we want to construct moduli space. I think this will appear as a problem when we want to try to construct moduli spaces. We need to find a solution for this problem. We do have some candidate, but there are too much of a speculation to come out with this, what could be an answer to the solution. So I'm just going to leave it like this for the time being. On the other hand, for foliation, rank 1 on a 3-4 situation is better. So somehow this is improves this result. So we show that flops do exist. This is also work in progress. So it's still under construction, but we do prove that flops exist for foliation of rank 1. Okay, so I don't know if I have time to say a few words about the proof. Let me just say very vaguely, because we're running out of time, what is the ingredients of existence of flips in the case of rank equal to 1? Why existence of flips somehow took us quite a lot of work. So very briefly, let's suppose that we have a curve which we expect to flip. So what is the hope? The hope is to find divisor delta, which is not too bad, and such that kx plus delta is negative with respect to this curve. Why? Because the reason why we do that is because once we do that, we can use existence of flips for varieties, and if delta is not too singular, if x delta is not too singular, we can find classic existence of flips to show the existence of what we want. So one thing that we proved 3 years ago, I mean, a couple of years ago, in the case of rank equal to 2, was that we don't need to do that on X, although the minimum of the program is still very, very open for formal schemes. I don't even know what the conjecture should be for generality. But at least in a formal neighborhood of C, the minimum of the program works. So if we can improve the existence of this delta in a formal neighborhood, then we can somehow run some kind of special minimum of the program and we get what we want. So this is good. Why? Because the idea that we wanted is to find a divisor which is invariant and then use a junction in such a way that this is true. Now, why do we need to work with formal neighborhoods? Well, because it's very hard to find separatrices. It's something like it's an invariant divisors on a variety, which are convergent, let alone on a Zariski open subset. So it's much easier, or at least it's more feasible to find these divisors on formal subschemes, formal neighbors of the curve. So, okay, let me skip some details, but let me just say that what is going on here is that, okay, I will just conclude by words so that I don't take too much time. So what do? We first construct the contraction of C. This is going to be an algebraic space, but this is good enough to descend to this guy here. So in order to do this, we need to use something like Shogorov complements, because we cannot just descend the canonical divisor of F, because this might not be Q-Cartier. Why do we do that? The reason why we do that is because it's much easier to find the invariant divisor downstairs. Why? Because to find a curve, to find invariant divisors which contain a curve, even on a formal neighborhood, is not easy at all. It's much easier to do it if we just look around a point, on a formal neighborhood of a point. So downstairs is better. And then somehow we lift them upstairs. Now, the problem is that we have no control whatsoever on the singularities. So we need to prove some properties about some kind of invariance, inversion of junction for pairs that comes in this way. But okay, maybe this is too technical, so I stop here. So thank you very much for your attention.
Thank you very much for the very nice talk, Paolo.
Thank you. So let me conclude by saying thank you.
Are there any questions? So Vanya, do you have a question? No, I see a raised hand, so I thought you wanted to say something.
No. I uploaded.
Ah, okay, sorry. Okay, so let's thank Paolo again.
Thank you. Thanks.
Thank you very much, Paolo. So I will terminate the meeting now.
Okay.
Thank you, Paolo. Bye.
Thank you.
Thank you,
Thank you, everyone. Bye-bye. See you later.